Myself, Nimisha J. Patel, Assistant Professor in Electrical Department of Mahatma Gandhi Institute of Technical Education and Research Center, Navsari. I deliver a video lecture on Power System 2. Today we learn about the chapter number 3, Transmission Line Modeling and Performance, and in this chapter we learn method of voltage control. In this method, reactive power injection, static var generator, rotating var generator, control by transformer, and reactive power compensation. Method of voltage control. Practically, each equipment used in power system are rated. Okay, all equipments are installed in power system. Okay, all installed equipments are as per their ratings requirement, as per this requirement and their ratings also. Okay, now these ratings, the equipment of ratings of these equipments is fixed. Okay, so when running the power system, okay, when supply the power system at sending end, okay, that times the connected the equipments with a transmission line all are run in a limited power voltage. Okay, limited their voltage is permissible band. Okay, now if the equipment is run in above voltage, that means this condition is called the over voltage, and that over voltage create the problems on equipment, so damage the equipment. Same as under voltage uh, condition is also damage the equipment. Okay, so all equipments are run in rated voltages. Okay, so take here the two bus system. First is sending end voltage, Vs have a angle delta, and sending end complex power Ps plus jQs, same as Vr is a reference voltage, so Vr with angle 0, complex power receiving end is Pr plus jQr, and load is Pd plus jQd. Okay, now this in this figure, the sake of simplicity, let the line be characterized by a series reactance. Okay, means it has a negligible resistance. Since the torque angle delta is a small under practical condition, real and reactive power delivered by the line for a fixed sending end voltage, the specified receiving end voltage can be rewritten as equation number 5.71 and 5.73. Means here the equation of receiving end power is equal to Vs into specified, in form of specified receiving end voltage. So equation is PR is equal to Vs specified receiving end voltage divided by X into sine delta. Same as specified reactive power is equal to specified reactive voltage divided by X in the bracket Vs minus specified receiving end voltage. Now equation of receiving end reactive power quadratic solution can be rewritten as, from this equation we write the specified receiving end voltage Vrs is equal to 1/2 Vs plus 1/2 Vs in square root of 1 minus 4 xq QR. This QR is a specified receiving and reactive power divided by Vs now square. Since the real power demanded by the load must be delivered by the load, PR is equal to PD. Demanded load means demand is equal to receiving and load. So varying real power demand PD is met by consequent changes in the torque angle delta. It is however to be noted that the receiving and reactive power of the line must remain fixed. Receive the reactive power of the line must remain fixed. Okay, that means when at a receiving specified receiving and reactive power as a given equation for fixed Vs and specified receiving end voltage. The line would therefore operate with a specified receiving end voltage for only one value of QD, given by QD is equal to specified receiving and reactive power. So here is the practical load are generally lagging in nature and are such that the VAR demand means QD. Reactive demand may exceed specified receiving and reactive power. It easily follows from equation number 5.83. Then for QD greater than specified reactive power at the receiving end, the receiving end voltage must change from the specified value to same value VR to meet the demand VARS. Okay, what is the practical load are generally lagging because of we all know the induction motors all industrial load are inductive load. So here generally the power system load is what is lagging in nature and are such that the VAR demand QD may exceed the specified reactive power at receiving end. It easily follows from the equation that for a QD greater than receiving end, specified receiving end reactive power, the receiving end voltage must change from the specified value. Change the value of specified VR to some value of VR. Okay. So some value of VR to meet the demand VARs. That means QD is equal to QR is equal to VR by X into Vs minus VR, where QD greater than specified QR. The modified VR is then given. VR is equal to 1 half Vs plus 1 half Vs from the equation square root of 1 minus 4xqr divided by Vs square. Okay. The comparison equation of 5.85 and 84. 84 and 85. Okay. Reveals that for a QD is equal to QR, demand is equal to receiving and reactive power is equal to specified reactive power. The receiving end voltage is specified receiving end voltage, but for a QD is equal to QR greater than specified reactive power. Okay. So Vs less than VR less than specified receiving end voltage. Now VR demand larger than specified reactive power is met by a consequent fall in receiving end voltage from the specified value. Similarly, if the VAR demand is less than specified receiving and reactive power, it follows the VR greater than specified receiving end voltage. Under light load condition, the charging capacitance of the line may be cause the VAR demand to become negative, resulting in the receiving end voltage exceeding the sending end voltage. Okay, we already studied in previous lectures. In order to regulate the line voltage under varying demands of VARs, the two methods discussed below are employed. First is a reactive power injection. In reactive power injection, two method we use: VAR generator, static VAR generator, and rotating VAR generator. Now we see the reactive power injection. It follows from the above discussion that in order to keep the receiving end voltage at a specified value, a fixed amount of VAR, means specified QR, must be drawn from the line. To accomplish line under condition of a varying VAR demand QD, a local VAR generator control reactive power source compensating equipment must be used, shown in figure. In figure we saw the, here is the VR receiving end voltage, here is the receiving end power, and here is the load power. Okay, so for this load we connect the local VAR generator in this manner. Okay, so here is the QRS, means specified reactive power, plus QC. QC is what is, here is the reactive local reactive generator. Okay, so here is the QC is equal to your QD. Okay, so fluctuation in QD are absorbed by the local VAR generator QC such that VAR drawn from the line remain fixed. Okay, demand fluctuation in demand is absorbed by this. So specified reactive power is fixed. The receiving end voltage would thus remain fixed at specified receiving end voltage. This of course assume a fixed sending end voltage Vs. Now local compensation can in fact be made automatic by using the signal from the VAR meter installed at the receiving end of the line. This system is what is automatic, and local VAR compensation can be made automatic by using the signal of VAR meter, and VAR meter is connected in receiving end side. Okay, from this meter the signal is changes. Okay, and VAR compensation is done. The two types of VAR generation are employed in practice: static type and rotating type. Now first we see the static VAR generator. It is nothing but a bank of three-phase static capacitor and or inductor. With reference to figure, this figure here is the receiving end bus, and for a QC is a what is, for a compensation, here is the static capacitor bank is connected. Okay, with reference of figure, if VR is in the line kilovolt and XC is in per phase capacitive reactance of the capacitor bank, XC is the per phase capacitive reactance of the capacitor bank, on the equivalent star basis, the expression for the VAR fed into the line can be derived as, means IC is equal to what is, voltage divided by reactance. What is voltage? VR, and reactance means VR by root 3, phase voltage, and XC is the reactance. So QC is equal to what is, 3 phase QC is equal to 3 VR by root 3 into minus IC conjugate. So multiplication, put the value of IC. So QC is equal to what is, J3 into VR by root 3 into VR root 3 XC into MVA. Okay, Here is the J. Okay. So we write the J here. Okay. Now QC three phase is equal to VR square divided by XC and VAR. Okay. VR and VR square this equation, and root 3 cancel. Root 3 is equal to 3. Cancel by 3. So equation become what is? VR whole square divided by XC MVAR. If includes are employed instead, VAR fed into the line R, QL is equal to minus VR square divided by XL. Okay. So here is the under heavy load condition, when positive VAR needed, capacitor bank are employed, and while under light load condition, when negative VARs are needed, that times inductor banks are switched on. Okay. For a positive VAR, we connected the capacitor bank, and for a negative VAR, we connected the inductor bank. Okay. The following observation can be made for a static VAR generator. Capacitor and inductor banks can be switched on in steps. However, stepless VAR control can now be achieved using SCR circuitry. Okay. Capacitor and inductor banks can be switched on in steps. So stepless means smooth VAR control can be achieved using silicon control rectifier. Since QC is proportional to the square of terminal voltage, means from this equation we see the QC is proportionally equation to square of terminal voltage. So for a given capacitor bank, their effectiveness tends to increase as the voltage sags under full load conditions. Third is, if the system voltage contains appreciable harmonics, the fifth being the most troublesome, the capacitors may be overloaded considerably. What is? If the system voltage contains the harmonics, okay, system voltage contains the harmonics, that time the fifth harmonics being the most troublesome, then the capacitor may be overloaded considerably. Okay. Now capacitor act as short circuit when switch on. Okay. We already known capacitor act as a short circuit when switch on, and inductor is open circuited when switch on. Okay. There is a possibility of series resonance with the line inductance, particularly at harmonic frequency. Okay. Here is there is a possibility of series resonance with the line inductance, particularly at harmonic frequency. Okay. Now rotating VAR generators. It is nothing but a synchronous motor running at no load and having a excitation adjustable over a wide range. Okay. Here we connected in static VAR capacitor bank, and here what we connected, a synchronous generator connected. It feeds positive VAR into the line and overexcited condition, and feed negative VAR when unexcited underexcited condition. Okay, overexcited condition, what we do, it is the positive VAR into the line, and under excited condition negative VAR in the line. A machine thus running is called a synchronous condenser. Here is the adjustable excitation. Figure shows a synchronous motor connected to a receiving end bus bar and running at no load. Okay. Since the motor draws negligible real power from the bus bar, no load, so the machine draws the negligible power. EG and VR are nearly in phase. XS is the synchronous reactance of the motor, which is assumed to have a negligible resistance. If EG and VR are in line kV, we have a IC is equal to VR minus EG with angle 0 degree divided by root 3 into J into XS kilo ampere. Okay. Now JQC is equal to 3 VR with angle 0 root 3 into minus IC. Put the value of IC. So equation becomes JVR EG minus VR divided by XS MVA. So QC is equal to what is? VR in the bracket EG minus VR divided by XS MVAR. Okay. It is immediately follow from the above relationship that the machine feeds positive VAR into the line where EG greater than VR, that means in overexcited case, and inject negative VAR if EG less than VR, where the underexcited case. Okay. VAR are easily and continuously adjustable by adjusting machine excitation, which controls EG. Okay, here is adjustable excitation. We change the excitation and control the VARs. Okay, means control the voltage. In contrast to static VAR generation, the following observations are made in respect to the rotating VAR, means compare of two VARs. This can provide both positive and negative VARs which are continuously adjustable. Okay. VAR injection at a given excitation is less sensitive to change in bus voltage as VR decreases and EG minus VR increases with consequent smaller reduction in QC compared to the case of static capacitor. From the observation made above in respect of static and receiving VAR generators, it seems that rotating VR generators would be preferred. However, economic consideration, installation and maintenance problem limit their practical use to such buses in the system where a large amount of VAR injection is needed. Okay. Now controlled by transformer. The VAR injection method discussed above lacks of flexibility and economically of voltage control by transformer tap changing. Okay, VAR injection method we discuss. There is a lack of flexibility and economically it is a not a refer. So we have another option to control voltage control by transformer. Okay, by transformer tape changing. We use the tape changing transformer in a practical way in the machines. Okay, when we use the experiment the practicals, that times what we do, first we apply the some voltages, small voltages, and then we increase the voltages. Okay, we do the increases voltage is in by through the auto transformer. Okay, through the auto transformer we change. In auto transformer numbers of tappings are available and we use the tappings as per the required voltage. Okay, So now we use the tap changing transformer. The transformer tap changing is obviously limited to a narrow range. Its range is small of voltage control. If the voltage correction needed exceeds this range, tap changing is used in conjunction with the wire injection method. For example, uh, we have used the tap changing transformer to 0 to 230 voltage. Okay, 0 to 230 voltage. So we change the voltage below the 230 voltage. Only we have a range of 0 to 230. So we have a range is 0 to 230. Below 230 we tap changes, means we have a tap changes at 5 voltage, 10 voltages, 15 voltages, etc. Means we control the voltages belongs below the 230 voltage. Okay, so here is the limitations. Narrow voltage range. So receiving end voltage which tends to sag owing to VARs demanding by the load can be raised by simultaneously changing the taps of sending end and receiving end transformer. Such tap changes must be made on load or off load. Here is the we use the on load tap changing and can be either manually or automatically. The transformer being called a tap changing under load transformer. Okay, what is tap changing under load transformer? Consider the operation of transmission line with a tap changing transformer at each end as shown in figure 5.13. This is a transformer. Okay, let TS and TR be the function of the nominal transformation ratio. That means tap ratio, nominal ratio. For example, a transformer with a nominal ratio is 3.3 kilovolt to 11 kV when tapped to give 12 kilovolt when 3.3 kV input. So here is the TS is equal to 12 by 11 is equal to 1.09. So here is a transmission line with tap changing transformer. Here is the transformer at sending end. Here is the receiving end, and line has a parameter Z is equal to R plus JX. Okay, here at receiving end and sending end, both types of tap changing transformer use. Okay, and its ratio is 1 gem TS by T1, and also here is the TS by 1 gem TS by I1 and TS by I2 gem 1. Okay, now with reference from figure, let the impedance of the transformer be lump Z along with the line impedance. Here is the Z is equal to R plus JX. To compensate for voltage in the line and transformer, let the transformer taps be set and off nominal value TS and TR. With reference to circuit shown, we have a TS into N1 into Vs. Okay, TS N1 into Vs means here is the what is the transformation ratio is equal to TS into N1, and here is the TR N2 gem 1. Okay, so here is the to compensate for voltage in the line and transformer, let the transformer tap be the set at off nominal value TS and TR. With reference, we have a TS N1 into Vs is equal to TR NR VR plus I into Z, means this voltage is equal to sending end voltage, what is TS into N1 Vs is equal to voltage drop here in the line, and sending end voltage is IRN2 into VR. Okay. Now from equation 5.75, the voltage is equal to voltage drop referred to the high voltage side is delta V is equal to RPR plus XQR divided by TR N2 into VR. Okay. So now delta V is equal to what is? Voltage drop is equal to sending end minus receiving end. Okay. So here is the sending end voltage and here is the receiving end voltage. Now put the value TS N1 into Vs. Okay. Multiplication by this. Okay. Is equal to TR N2 VR plus what is RPR plus XQR TR N2 into VR. Means we have a equation, this equation delta V. Put in this equation delta V. Okay. And find the value of this. Okay. Put this value here. So this equation goes to this side, so addition of delta V means TS N1 Vs is equal to TR N2 VR plus RPR plus XQR divided by TR N2 VR. In order that the voltage on the high voltage side of the two transformers be of the same order and the tape setting of each transformer with the minimum, we choose TR is equal to 1. So substituting this value TR is equal to 1 upon TS in this equation become TS square 1 minus RPR plus XQR divided by N1 N2 into Vs VR is equal to N2 divided by N1 VR divided by Vs. Okay. For a complete voltage drop compensation, the right hand side of equation should be unity. It is obviously from figure 5.30 that Ts greater than 1 and Tr less than 1. For a voltage drop compensation, equation number 5.90, this equation indicates that Tr tends to increase the voltage. That means delta V which is to be compensated. Thus, merely tap setting as a method of voltage drop compensation would give a rise to excessively large tap setting if compensation exceeds certain limits. Thus, if the tap settings dictated by equation 5.93 to achieve a desired receiving end voltage exceeds the normal tap setting range, usually not more than 20%, it would be necessary to simultaneously inject VARS at the receiving end in order to maintain the delivered voltage level. Okay, now compensation of transmission line. The performance of long extra high voltage AC transmission system can be improved by reactive compensation of series or shunt type. Series capacitor and shunt reactors are used to reduce artificially the series reactance and shunt susceptance of the line, and thus they act as the line compensators. Compensation of line results in improving the system stability and voltage control, in increasing the efficiency of power transmission line, facilitating line energization and reducing temporary and transient over voltages. Okay, we use the shunt or reactors or series capacitors used in an extra high voltage transmission line. We improve the performance of the transmission line. Okay, series compensation reduces the series impedances of the line, which cause voltage drop and is the most important factor in finding the maximum power transmission capacity of the line. Equation 5.17. That means A, C and D constants are function of Z and therefore the also affected by changes in the value of Z. But these changes are small in comparison to change in beta, as beta is equal to Z for the nominal pi and equal Z sine hyperbolic gamma L divided by gamma L for the equivalent pi. Okay, so the voltage drop delta V due to series compensation is given by delta V is equal to IR cos phi R plus I into XL minus XC sin phi R. Hence, the XC is equal to what is capacitive reactance of the series capacitor bank per phase, and XL is the total inductive reactance of the line per phase. In practice, XC may be so selected that the factor XL minus XC sin phi R becomes negative and equals magnitudes. Okay, that means we choose the XC. The value depends on value of XL. Okay, so R cos phi R, so that delta V becomes 0. The ratio XC divided by XL is called the compensation factor, and when expressed as a percentage is known as the percentage compensation. Okay, the extent of the effect of compensation depends on the number, location and circuit arrangement of series capacitor and shunt reactor stations. While planning long distance lines, besides the average degree of compensation required, it is required to find out the most appropriate location of the reactor and capacitor banks. So the optimum connection scheme and the number of intermediate stations for finding the operating condition along the line, the ABCD constants of the portions of this line on each side of the capacitor bank, and ABCD constants of the bank may be first found out, and then equivalent constants of the series combinations of the line capacitors line can then be arrived at by using the formulas given in appendix B. Okay, in India, in states like UP, series compensation is quietly important since super thermal power are located several hundred kilometers from the load centers, and large chunks of power must be transmitted over long distance. So series capacitors also help in balancing the voltage drop of two parallel lines. Means here what we study, the control of voltage, means we control the voltage and voltage drop. Okay, for this we use the compensation of transmission line. When series compensation is used, there are changes of sustained over voltage to the ground at the series capacitor terminals. This over voltage can be the power limiting criteria at high degree of compensation. A spark gap with a high speed contactor is used to protect the capacitor under over voltage conditions. Okay, over voltage condition, what we use? A spark gap with a high speed contactor to protect the capacitors. Okay, under high load or no load condition, charging current should be kept less than the rated full load current of the line. The charging current is approximately given by BC into V, where BC is the total capacitive susceptance of the line and V is the rated voltage to neutral. So, if the total inductive susceptance is BL due to the several inductors connected from line to neutral at appropriate places along the line, then the charging current would be I charging is equal to BC minus BL into V is equal to BC into V 1 minus PL by BC. Okay. It may be noted that for the same voltage boost, the reactive power capacity of a shunt capacitor is greater than that of the series capacitor. Okay. It may be noted that for the same voltage boost, the reactive power capacity of a shunt capacitor is greater than that of the series capacitor. So the shunt capacitor improves the power factor of the load, while the series capacitor has hardly any impact on the power factor. So series capacitor are more effective for a long line for a improvement of system stability. Thus we see that in both series and shunt compensation of a long transmission line, it is possible to transmit large amount of power efficiently with a flat voltage profile. So proper type of compensation should be provided in proper quantity in appropriate places to achieve the desired voltage control. Okay, means for a voltage control we use the compensation method, shunt and series capacitor. Now the question, why we need to voltage control? Explain voltage control method, explain the compensation of transmission line, and explain the static var and rotating var generators. Okay, thank you.